Before we can discuss more sophisticated measures of quantum entropy in information, we first have to understand the basics of entropy and how it's measured in quantum mechanics. To begin, let's review our classical understanding of entropy. Generally, entropy is a measure of the uncertainty or randomness of a physical system. Some information theorists also regard entropy as a measure of how much information or knowledge a physical system is carrying at a particular time. This is because the information extracted from a more random or chaotic system is generally more valuable than that is extracted from a more predictable or uniform system. To put all this mathematically, consider a system which has n states where the system has a probability pi of being found in each particular state I. In thermodynamics, we can define something called the Gibbs entropy as the sum of the probabilities multiplied by their logs. And we add in an extra constant, namely the Boltzmann constant, to arrive at the correct units. And this Gibbs entropy is, again, it gives us a numerical value to measure that uncertainty or randomness that we're interested in. In statistical mechanics, it is more common to use the Shannon entropy, which has roughly the same form, it just doesn't include the proportionality constant. In this slide, I've expressed the Shannon entropy as an expectation value, i.e. in the lingo of quantum mechanics, but its form is the same as that of the Gibbs entropy. Note that if our system is continuous, then these summations would become integrals. Luckily, in the case of the Shannon entropy on the right, the Dirac notation encodes this for us quite nicely. To transition this classical understanding of entropy to quantum mechanics, we first have to introduce a few concepts. Namely, we first need to discuss the notion of pure and mixed states. So a pure state is a state that can't be expressed as a probability mixture or convex combination of other states. This means that there's no combination of states whose coefficients sum to 1. By contrast, a mixed state is a statistical ensemble of pure states. Note that a quantum superposition, like we can see on the left, is not the same thing as a mixed state. Superposition represents the state of a single system where the system itself can be in multiple possible states at once. If the system were composed of two states in superposition with probability amplitudes of 50% each, we would obtain a wave function like the one on the left that we're all pretty familiar with. Such a wave function still corresponds to a single system in a pure state. A mixed state, by contrast, is an ensemble of multiple systems. We're performing measurements on each of the various systems that can be prepared in a number of different ways, sort of like a distribution. For example, a mixed state of a two-state system where the system has a 50-50 chance of being prepared in either one state or the other when you measure it would look like on the right, what we see on the right, which is just a set of different states. This is in contrast to superposition, where a single system is in both states at once until it is measured. So, to put this notion of pure and mixed states more mathematically, we need to introduce the idea of a density operator. So, a density operator is just a way of representing a mixed state system. We can define it as a probability weighted sum of the outer products of all the pure states that make up the system. So this formulation allows us to see a more obvious mathematical distinction between pure states and superposition. A pure state has a density operator, which is just a single outer product, right? It's just one pure state mixed with itself, as you can see on the top. In contrast, or conversely, a mixed state has multiple terms in its expansion for the density operator, each with their own probability, which you can see on the bottom. And so we can see, obviously, that these two concepts are distinct from one another. Finally, we can put all this together to define the von Neumann entropy, which is the quantum analog of the Shannon entropy. In fact, if the probabilities are the eigenvalues of the density operator, then the von Neumann entropy effectively becomes the Shannon entropy. It has a similar interpretation to the Shannon entropy. It is the uncertainty or randomness of a mixed quantum system. Notice, by the way, that if the system only is in a pure state, then the von Neumann entropy is 0. And just to clarify on the notation there, that TR refers to the trace. So building on this framework of pure, mixed, and mixed states and density matrices, we can now go on to introduce some more sophisticated measures of quantum entropy.
All right, now that we've defined general measures of quantum entropy, I would like to focus and discuss a specific and very interesting new measure of entropy that actually approaches its classical definition in the semi-classical limit, and that is the Ks entropy. So I would like to first start off with a discussion of the classical definition of chaos entropy, as it varies pretty significantly from the regular Boltzmann definition of entropy. So the chaos entropy or metric entropy was first defined when physicist Andrei Kolmogorov was trying to distinguish between systems that were only defined by ODEs that are completely deterministic compared to sort of stochastic differential equations. So, given this, to define the KS entropy of the system, we first examine some partition in phase space, and as the partition in phase space changes over some discrete time interval, there are many possible for each trajectory within the partition. There are many possible different trajectories it can go because it's not completely defined because there's some stochastic element. So what we do is take the Shannon entropy over all trajectories within that partition, and that defines the KS entropy for that one partition. Then to get the KS entropy of the entire system, we take the Sapernium, so the greatest possible, the lowest, the least upper bound of the KS entropy given possible for any given possible partition. So this is a very theoretical concept. It's not really something you could. It's not easily measurable in the lab, but it does tell us how random a system is, how predictable the system is, and sort of how much information we can get out of it. So that is defined. The Shannon entropy for the different probabilities is defined by this equation below. So as we can see, it's not as very clear how we would derive uh, the quantum analog to this because we can't really have phase space and partitions, and quantum phase space is quite odd. So we will just start off by looking at the KS entropy for just some given initial starting point, which is defined by this. So some initial starting point with some regular Hamiltonian coupled to some weak noise, because that will come in later when we start coupling our quantum system to weak noise. So as you can see, the KS entropy for it, where the dimension is Q over some particular dimension, is given by this equation, which can be rewritten as the Renier entropy. So the KS entropy is actually the time rate of change of the Renier entropy, which is useful because the Renier entropy is actually defined in the quantum sense. So as we can see, this is the equation given for the Renier entropy of a single starting point, and then the KS entropy is essentially the um, time evolution of the Renier entropy. And this the dy dt is actually can be thought of as a probability cloud. So given some initial starting point, all the infinite possibilities sort of expand in a cloud at some later time t. We can then take the expansion of that cloud, right, as that probability cloud expands in space. We can take the entropy of that, or the KS entropy of that, and the variance of that cloud, and that will describe the KS entropy for that initial starting condition. And in the final equation I described, it defines the variance of the cloud as as the determinant of some 2x2 matrix, which is A sub t, and then that over T naught is just some initial starting point, so that it's normalized at some initial starting condition. And then now that we've got it, so now that we sort of understand the KS entropy is really talking about how much the probability cloud of some initial trajectory happens over time, we can start working and start describing the KS entropy. And to do this, we actually start off with the Renier entropy, because we know it should be the time rate of change of the Renier entropy. And using second order time dependent perturbation theory, we consider a system where we have some quantum state or some quantum evolution that is then instantaneously coupled to a auxiliary heat bath. So like most quantum experiments happen in place, when almost absolute zero temperatures. So this example, this was defined because we can kind of go from what we know is a relatively low and not as chaotic state into a more chaotic state, and really will help us understand more of the open sort of open quantum systems and how decoherence happens. So as we can see, I obviously won't be able to go through the entire derivation, but given the Rényi entropy, we can define some matrix, matrix A, which is similar to the matrix A that we described earlier, which is taking where x of t in this x of t in this equation is the coupling to the heat bath, and phi naught is the initial pure state. So as the as the so the coupling grows, as the coupling to the auxiliary heat bath grows and affects the pure state more, we can see the probability cloud changes and expands, and that's reflected in this equation where we have some 1 plus epsilon squared tau. But that's not really important. It's essentially telling us that the expansion and the coupling to the heat bath over the wave function defines the Ks entropy of the system, which is also convergent to the classical definition in the semi-classical limit. So essentially, if we take a limit as h bar goes to 0, we see that the equation converges to its classical definition, which is super useful because via the Pessin relation, we know that the Ks entropy should just be the sum of all positive Lyapunov exponents. So if we were to try and define some quantum Lyapunov exponent, it would also have to equal the Ks entropy of the system, which we have defined in this case. But there are a few problems with this definition, and I would say the largest problem would be the time scale. When solving for this problem, we assume that epsilon would be small, relatively small. But if you set epsilon to 0, then this equation doesn't really make any sense. So we have to choose a time frame where the that's not so long that it would be completely random and completely classical, or and we can't choose it so small that epsilon would be small enough to make the equation not understandable. So the authors of the paper that I referencing was able to define some time frame, and it actually seems like this issue with timescale is reflective of any quantum Lyapunov exponent. So in some capacity, even though the timescale seems weird, it actually has actually an expected thing to happen. So moving on, this is useful and informative because it will help us define some quantum Lyapunov exponent, but it'll also help us to understand and define more connected thermodynamic quantities, and some that might actually be measurable in real life.
Quantum Fisher information. Quantum Fisher information is a measure of how precisely a measurement can be performed on a quantum system. It is particularly useful for mixed states, where it plays a large role in the field of quantum metrology. Quantum metrology aims to make highly sensitive measurements of parameters in quantum systems and relies on quantum parameter estimation, which in turn uses the Cramer-Rao bound. This bound is determined using the quantum Fisher information matrix, which sets a limit on the accuracy of quantum estimation. Quantum Fisher information has many other uses, such as in spinor systems, quantum dynamics, quantum thermometry, entanglement detection, and a lot of others. So firstly, in order to fully understand quantum Fisher information, we first need to understand the classical Fisher information can be thought of as the amount of information an observable carries about a parameter. In the case of n parameters, the classical Fisher information is defined as a diagonal entry of the classical Fisher information matrix. And the entries of this matrix are calculated using the equation shown on the slide here, where x is the vector of parameters, p of y and x is the conditional probability for the outcome. Using what we know about classical information, we can then find a similar equation for the quantum Fisher information. So, given the eigenvalues of the density matrix, the entries of the quantum Fisher information matrix are given by the top equation on the slide here. and the value S is the support of the density matrix operator. The quantum Fisher information is given as the diagonal entries of the matrix, and the bottom equation shows the calculation for the QFI of parameter A. If we could compare these two equations to the equation on the previous slide, we can see that the first term here is analogous to the calculation for the classical Fisher information matrix, but the second two terms arise as a result of purely quantum effects. So, one of the uses for quantum Fisher information is determining if the Cramer-Rao bound is attainable. The Cramer-Rao bound is important to the field of quantum metrology because it provides a bound in the achievable precision of a parameter estimation in a quantum system. The multi-parameter Cramer-Rao bound is given by the equation on the slide here, which can be derived using the Heisenberg uncertainty principle. The left side of this equation is the covariance matrix of an unbiased estimator under a set of positive operator bounded measures. And on the right side, N is the number of repeated experiments, and F is the quantum Fisher information matrix. The quantum Cramer-Rao bound can sometimes be difficult to find for multi-parameter systems because each parameter has a different operator measurement, which may not commute with one another. Quantum Fisher information is particularly interesting in the field of entanglement as it can provide a criterion for whether or not mixed-states are entangled. It can be powerful when used in conjunction with the known criterion for entanglement based on variance. And for a pure state, the QFI does reduce to the variance. It has long been known that variance can be used to show whether or not two states are entangled, but in 2013, we showed that it was possible to derive a criterion for entanglement based on the quantum Fisher information. In particular, the condition for entanglement they found is given on the relation here. This relation works for any bipartite m by n dimensional state rho and any local orthonormal observable bases A and B. When this inequality is satisfied, we can detect entanglement using QFI. In a basic example, this criterion was used to prove the entanglement of the Bell states, which can also be shown using other methods. However, in an example in which the criterion based on variance failed to identify entanglement in a mixed state, the one based on QFI correctly identified the entanglement. This shows that this criterion based on variance is not always enough, and sometimes we need other ways to detect entanglement, such as a criterion based on QFI. So, just to wrap up, QFI has a range of uses, such as for quantum estimation and detecting entanglement. There are several questions we still have today about quantum mechanics, such as finding optimal measurements and understanding entanglement for mixed states, both of which can be answered in part by QFI. There are many other fields in which QFI may be able to further our understanding of quantum. So that's all on quantum Fisher information. So thank you.